One of the things that we can look at is we can look at what's called the entropy of a system. And what this is it's a statistical measure of the amount of randomness or disorder that is associated with a reaction. Now, the greater the disorder or randomness in and of itself doesn't tell us a lot, but it helps us to remember that this is a take on the second law of thermodynamics. It says that when I have a change of energy, it's going to cause an increase in disorder. And so we can calculate our entropy value similar to how we calculate our enthalpy value with our standard enthalpy of formations. And we can see at the bottom our reaction. So let's take a look at this example where we calculate the entropy of the reaction of urea with water to form carbon dioxide and ammonia. Okay, now we will answer this question in exactly the same way as we answer other questions, or the enthalpy questions specifically. So the first thing we need to write a balanced chemical equation. Then we'll write down our givens, and these values can be looked up in a table just like our standard enthalpy of formation values. Then we can write down our equation, and we can substitute in, and we can solve. And so this type of question is just like how we calculated our enthalpy value with our standard enthalpies of formation, but the one thing I want to point out is the units. At the end, my units are in joules per Kelvin. Now, this value in and of itself isn't of much interest, but it is of interest because it comes into play with Gibbs free energy. Now, Gibbs free energy is a value where we look at the amount of energy change when my system undergoes a reaction, and whether it's endothermic or exothermic, as well as a change in order or disorder. And what we can think of is we can think of Gibbs free energy as the amount of free or useful energy available after this reaction takes place. And the more energy that's available, the more likely the reaction is to be spontaneous. And so if I have a delta G, or a change in Gibbs free energy that is less than 0, my reaction will be spontaneous. So if we go back to our example of the reaction of urea with water, we can determine whether or not the reaction was spontaneous or not by looking at the change in our free energy. Just like before, first thing we need is a balanced chemical equation. Then we have to look up our givens. And now we could calculate both our enthalpy and entropy values using their appropriate equations. Now, we already knew the entropy value, but we also have our enthalpy value here. And I'm going to point out again, look at the difference in units. So we're going to have to make sure that we convert this to kilojoules before we use it. And then we can substitute into our equation for determining our Gibbs free energy. Now we notice that temperature is important because the temperature affects the amount of randomness that a system will have. And so as a result, we see that our free energy change is a positive value. And so what that tells us is this would not be a spontaneous reaction. And therefore we would have to add energy, and we would have to add some other stuff to get this reaction to occur. When we want to look at reactions in general, we can come up with a general summary of if a reaction will be spontaneous or not. So for example, if my enthalpy value is negative and my entropy value is positive, I'll always have a spontaneous reaction. If my enthalpy value is positive and my entropy value is negative, I'll never have a spontaneous reaction. And then my other combinations will be dependent on our temperature.